Hello, and welcome. Perhaps you're lying in bed right now, the light from your screen the only glow in the darkness. Or maybe you're sitting quietly, looking for a moment of calm in a day that felt too loud, too fast. Either way, you're here, and that's enough. Tonight, we're going to explore something remarkable together. Something that happened recently, quietly, in a laboratory cooled to temperatures colder than the void of space itself. A barrier broke, not with fanfare or headlines screaming across the world, but with the soft hum of equipment and the patient satisfaction of scientists who'd been chasing this moment for decades. The barrier was one that physicists had proven, mathematically, shouldn't be breakable. The kind of limit that wasn't just engineering, it felt fundamental, woven into the fabric of how reality permits information to exist and survive. And yet it broke. What does it mean when the impossible becomes possible? Not in fairy tales or imagination, but in the measured, careful world of quantum physics. What happens when reality itself seems to rewrite its own rules, right there in the data, undeniable and strange? We're going to drift through this question together, slowly, with no rush to arrive at answers, because sometimes the most beautiful thing isn't the answer, it's the wondering itself. The gentle recognition that the universe remains larger and stranger than we suspected. So settle in, get comfortable, let your breathing slow. We have time. There's something almost rebellious about the quantum world, a refusal to follow the rules that seem so obvious, so inevitable in our everyday experience. Think about anything in your room right now, a book on a shelf, a cup on a table. Each one exists in a specific place, in a specific state. The book is either open or closed. The cup either holds water or it doesn't. This feels like the fundamental nature of things. Objects are what they are, where they are, doing what they're doing. But shrink down, go smaller than cells, smaller than molecules, down to individual atoms and the particles that compose them. Here, reality stops obeying those comfortable rules. Here, particles don't just refuse to have definite positions, they seem to actively exist in multiple states at once, in a phenomenon we call superposition. The most famous demonstration of this strangeness is the double-slit experiment. Send a single particle, a photon of light or an electron, toward a barrier with two narrow slits. Common sense says it must go through one slit or the other, but when scientists actually look at the pattern these particles create over time, something impossible appears, an interference pattern, the kind that only emerges when waves pass through both slits simultaneously and overlap with themselves. A single particle going through both slits at once. It's not that we don't know which slit it went through, it's that the very question seems to dissolve at this scale. The particle exists in a superposition of both paths until something, an interaction, a measurement, an observer, forces it to choose, to collapse into one definite history. This isn't a trick or an approximation. It's been verified in thousands of experiments across a century of physics. It's the foundation of all matter, including you, including the device you're holding, including everything. The quantum world is the real world. Our comfortable classical intuitions are just what happens when you zoom out, when trillions upon trillions of quantum possibilities average together into the solid, predictable experience we call normal life. Why does matter behave this way? No one fully knows. The mathematics works perfectly. Quantum mechanics is the most precisely verified theory in all of science. But what it means philosophically remains deliciously uncertain, and it's on this strange, probabilistic foundation that scientists are trying to build computers. Not just any computers, but machines that harness superposition itself, that compute by existing in many states simultaneously. Which brings us to the first problem. Quantum states are extraordinarily, almost impossibly fragile. Imagine trying to hear a whisper in a hurricane. That's what it's like to maintain quantum information in our warm, chaotic universe. Decoherence, the word physicists use for quantum states collapsing, happens because quantum systems are sensitive to everything. A stray photon bouncing off an atom, a vibration traveling through the material, a fluctuation in a magnetic field, even the thermal energy of normal temperature, the random jiggling of molecules in the air around you, is enough to destroy quantum coherence in microseconds. The quantum state doesn't just fade or degrade, it evaporates. One moment, your particle exists in a delicate superposition of multiple states. All the computational power you were hoping to harness concentrated in that impossibility. The next moment, it's collapsed, chosen a single state, and all that potential has vanished into irretrievable randomness. Building a quantum computer means creating a space so isolated, so quiet, that quantum information can survive long enough to actually compute something useful. It means cooling systems to within a few thousandths of a degree above absolute zero, colder than interstellar space, colder than anywhere in the natural universe. It means shielding against vibrations so subtle you couldn't feel them with your hand, against magnetic fields weaker than Earth's, against photons from the ambient environment. You're essentially trying to hold smoke, not metaphorical smoke, something that dissipates the moment you touch it, that requires absolute stillness to even exist. Superconducting quantum computers use circuits chilled to 15 millikelvin, 15 thousandths of a degree above the coldest possible temperature. At that temperature, metal loses all electrical resistance, and quantum effects become visible at scales large enough to manipulate. But even there, even in that frozen stillness, decoherence creeps in. Coherence times, how long a qubit stays quantum, are measured in microseconds or, in the very best systems, milliseconds. A millisecond sounds fast to us, but computers operate on nanosecond timescales. A quantum computer with millisecond coherence is like trying to have a conversation with someone who forgets everything they said a minute ago. You can't build anything complex. You can't chain operations together. The information evaporates faster than you can use it. Other approaches exist: trapped ions held in electromagnetic fields, quantum dots in semiconductors, topological qubits that encode information in properties that should theoretically be more resistant to noise. Each has advantages, each faces the same fundamental enemy. The universe doesn't want quantum states to persist. Classical computers fail gracefully. A bit flips from 0 to 1, you might get a wrong answer, but the computer keeps running. Quantum computers fail catastrophically. Decoherence doesn't just introduce errors, it destroys the very thing that makes the computer quantum. You're not just losing data, you're losing the computational advantage entirely. And worse, when you try to scale up, when you add more qubits to solve bigger problems, you're also adding more opportunities for decoherence, more particles to isolate, more interactions to control. The noise multiplies faster than your computational power. This is why, for years, quantum computing felt like trying to build a sandcastle as the tide comes in. Classical computers have a beautiful solution to errors: redundancy. Copy your data across multiple bits, check them against each other. If one flips, the majority vote tells you what the original value was. Fix it, continue. This is how your laptop, your phone, every digital device you've ever used maintains reliable computation despite imperfect hardware. Quantum computers can't do this. There's a theorem in quantum mechanics, the no-cloning theorem, that proves you cannot make a perfect copy of an unknown quantum state. It's not an engineering limitation, it's a fundamental law of physics, proven with the same rigor as conservation of energy. You can't back up quantum information the way you back up files on your computer. So how do you protect it? How do you fix errors without measuring the quantum state, which would collapse it and destroy the very information you're trying to preserve? This is where quantum error correction becomes, paradoxically, both essential and seemingly impossible. Every operation you perform on a qubit, every quantum gate, every manipulation, has some probability of error. Superconducting qubits, the kind used in most current quantum computers, have error rates around 0.1% to 1% per operation. That sounds good. 1 error per 1,000 operations, but quantum algorithms require millions of operations. String together a million operations with a 0.1% error rate per operation, and you're virtually guaranteed to have accumulated errors that completely corrupt your result. Classical error correction brings error rates down from, say, 1 in 1,000 to 1 in a billion or better. Quantum error correction tries to do the same thing. But the approach is wildly different. Instead of copying qubits, you spread the information across multiple physical qubits in a clever entangled state, a logical qubit. You can measure certain properties of this entangled state to detect errors without measuring the information itself. When you find an error, you correct it. In theory, this works. The mathematics is beautiful and sound. In practice, it requires something absurd. Your error correction operations must themselves be more accurate than the errors you're trying to fix. If fixing errors introduces more errors than you started with, you've created a death spiral. More qubits mean more operations to maintain them, more operations mean more errors, and the whole system collapses into noise. Imagine trying to bail water out of a sinking boat with a bucket that has holes in it. If the holes leak faster than you can bail, adding more buckets doesn't help. It makes things worse. This is the loop that trapped quantum computing for years. Every attempt to add error correction required hardware so imperfect that the error correction itself became the primary source of new errors. Researchers could demonstrate error correction working on paper, in simulations, even in tiny experimental systems. But scaling up made things worse, not better. Some physicists began to wonder if this was a fundamental barrier, not just hard engineering, but a limit imposed by the structure of quantum mechanics itself. Maybe the universe simply doesn't permit large-scale quantum computation. Maybe decoherence, thermodynamics, and the fragility of quantum states add up to something that can't be overcome, no matter how clever the engineering. That thought, that maybe we were chasing something physically impossible, haunted the field until recently. There's a specific number that became almost mythical in quantum computing circles: 99.9%. This comes from something called the threshold theorem for quantum error correction. Proven in the late 1990s, it's one of the most important results in quantum computing theory. It says roughly, if you can get your physical qubit error rates below a certain threshold, and if your error correction protocols themselves are good enough, then adding more qubits will reduce errors instead of multiplying them. The threshold depends on your specific error correction scheme and the details of your hardware, but for most realistic implementations, it sits somewhere between 99% and 99.9% accuracy per operation. Below that threshold, error correction works. Above it, you're in the death spiral. For years, labs around the world were stuck at 99% or slightly above. Close, tantalizingly close, but not quite good enough, is the difference between bailing water faster than the boat sinks and just barely not keeping up. You can see the goal, you can almost touch it, but almost doesn't compute. The frustration was profound. Researchers could build better qubits, isolate them more carefully, calibrate their control pulses with greater precision. Error rates would drop from 2% to 1% to 0.5%. Each improvement took years of work, new materials, new techniques, entire PhD theses dedicated to shaving off another fraction of a percent, but the threshold remained out of reach, and without crossing it, quantum error correction was a beautiful mathematical idea with no physical implementation. Quantum computers remained science experiments, not practical tools. This is where physics and psychology intersect in strange ways. When you work on a problem for decades, when thousands of brilliant people push against the same barrier using every technique they can imagine, a kind of learned helplessness can set in. Maybe the barrier isn't just difficult, maybe it's fundamental. Thermodynamics places limits on efficiency. The speed of light limits information transfer. The uncertainty principle limits simultaneous knowledge of position and momentum. Physics is full of absolute boundaries. Was quantum error correction another one? Was there something about the nature of measurement, entanglement, or decoherence that made large-scale quantum computing physically impossible, not just technologically hard? Some researchers thought so. Papers were published exploring fundamental limits, analyzing whether environmental decoherence might impose constraints that no amount of engineering could overcome. The math suggested it should be possible, but math had been wrong before when meeting reality's full complexity. Others remained optimistic, but acknowledged the enormity of the challenge. Even if possible in principle, it might require such precise control, such extreme isolation, such perfect calibration that practical quantum computers would remain perpetually 10 years away. Fusion power's less famous cousin in the family of technologies that never quite arrive. The breakthrough would need to be decisive. Not incremental improvement, but a genuine crossing of the threshold. A demonstration that error rates actually decrease as systems scale up. Without that, quantum computing would remain a fascinating scientific curiosity, a window into quantum mechanics, but not a revolution in computation. The barrier felt fundamental because it was tied to the deepest strangeness of quantum mechanics itself. You're fighting against decoherence, but decoherence is just the universe being normal. Quantum states are the exception, the fragile bubble that requires extraordinary conditions. Classical physics is the default. Maintaining quantum coherence in a warm, noisy, thermodynamically chaotic universe isn't just hard, it feels like swimming against entropy itself. And yet, let's zoom out for a moment and look at what it actually takes to ask these questions. What the experimental apparatus of impossibility looks like. Somewhere in a laboratory, there's a cylinder of metal roughly the size of a large refrigerator. Inside it, nested like Russian dolls, are layers of increasingly extreme isolation. Each layer cools the next, shields the next, separates the quantum system at the center from the universe outside. At the outermost layer, the temperature might be room temperature, comfortable for the humans walking past. Move inward, liquid nitrogen cooling, bringing things down to 77 Kelvin, cold enough to freeze carbon dioxide solid. Inward again, liquid helium, 4 Kelvin, colder than anything in nature except the cosmic microwave background left over from the Big Bang. But that's not cold enough. Not even close. The innermost chamber uses a dilution refrigerator, a machine that exploits quantum properties of helium-3 and helium-4 isotopes to reach temperatures of 10 to 15 millikelvin, 15 thousandths of a degree above absolute zero. At this temperature, thermal energy is so low that quantum effects dominate even in macroscopic objects. Metals become superconductors, losing all electrical resistance. The distinction between quantum and classical blurs. Inside this frozen heart sit the qubits, superconducting circuits etched on silicon chips, Josephson junctions that create artificial atoms with quantum energy levels you can manipulate, or perhaps trapped ions, individual atoms held motionless in electromagnetic fields, their quantum states controlled with laser pulses tuned to impossible precision, or quantum dots, tiny crystals where single electrons trapped in semiconductor wells become the qubits. Each approach has its poetry. Superconducting circuits, the most common, are quantum mechanics made visible at human scales, centimeter-long wires behaving quantum mechanically. Trapped ions are the cleanest, most isolated qubits, individual atoms floating in vacuum, touched only by light. Quantum dots bridge the semiconductor industry's expertise toward quantum applications. All require extraordinary isolation, vibration isolation. The entire apparatus often sits on shock absorbers or active damping systems, protecting the qubits from footsteps in the hallway, trucks driving past outside, even seismic rumbles from distant earthquakes. Electromagnetic shielding, layers of mu metal and superconducting materials blocking stray magnetic fields. Optical isolation, darkness, absolute and complete, because even a single photon can decohere a qubit. The engineering is humbling. You're trying to create a bubble of perfect stillness in a universe that never stops moving, and even with all this, coherence times remain measured in microseconds to milliseconds. The quantum states you've worked so hard to create and protect exist for less time than it takes you to blink. Computation has to happen in that window, if it's going to happen at all. Standing outside one of these machines, you can't hear the quantum processes inside. No hum, no click, no indicator that anything is happening, just the occasional whir of pumps maintaining vacuum, the hiss of cryogenics, the soft sounds of complexity maintaining itself. Inside, at scales you can't see, quantum superpositions rise and fall. Entanglement spreads between qubits, gates pulse and information. Strange, fragile quantum information dances briefly before dissolving back into thermal noise. This is the stage on which the breakthrough happened. Not dramatically, not suddenly, but through accumulated patience, Thousands of adjustments, calibrations refined to parts per million, software algorithms learning the idiosyncrasies of each individual qubit. The barrier didn't shatter, it eroded, one careful improvement at a time, until finally the threshold appeared on the other side. Before we get to how the barrier broke, it's worth pausing to consider what waits on the other side. What becomes possible if quantum error correction actually works at scale? The promise of quantum computing isn't just faster. Classical computers can already do billions of operations per second. Speed alone isn't revolutionary. The promise is different: access to computational problems that are fundamentally intractable for classical machines, regardless of speed. Drug discovery, for instance. Understanding how a potential drug molecule interacts with proteins in your body requires simulating quantum mechanical interactions, electrons orbiting atoms, chemical bonds forming and breaking. Classical computers can approximate simple molecules, but complex pharmaceutical compounds involve so many quantum interactions that exact simulation becomes exponentially harder with each added atom. Quantum computers, simulating quantum systems with quantum systems, could explore chemical space with precision impossible otherwise. Material science faces similar limits. Room temperature superconductors, ultra-efficient solar cells, better batteries. These materials might exist, might be physically possible, but finding them requires understanding quantum mechanical behavior of electrons in novel crystal structures. The search space is incomprehensibly vast. Quantum simulation could navigate it directly. Cryptography gets darker and more interesting. Most of the encryption securing internet communication relies on the fact that factoring large numbers is computationally hard for classical computers. Finding the prime factors of a 2048-bit number would take classical computers longer than the age of the universe. But Shor's algorithm running on a quantum computer could do it in hours. Every secure transaction, every encrypted message, every digital signature, all potentially vulnerable. This isn't speculative. The mathematics is proven. Quantum computers of sufficient scale would break current encryption. Governments and corporations are already migrating to post-quantum cryptography, algorithms believed to resist quantum attacks. The threat isn't immediate, but it's real enough to drive policy changes now. Optimization problems, finding the best solution among countless possibilities, appear across logistics, finance, artificial intelligence, climate modeling. The traveling salesman problem. Find the shortest route visiting all cities exactly once. With 20 cities, there are about 10-18 possible routes. With 50 cities, more routes than atoms in the universe. Classical computers can approximate, use heuristics, find good enough solutions. Quantum computers might find optimal solutions by exploring the solution space in fundamentally different ways. Machine learning could shift as well. Training neural networks requires optimization across millions of parameters. Quantum algorithms might accelerate this, or enable entirely new architectures. Quantum neural networks processing quantum data in ways we can't yet imagine. The gulf between demonstration and deployment is vast. Showing that quantum error correction works doesn't immediately give you a drug discovery quantum computer. You need millions of logical qubits, each built from hundreds of physical qubits. You need quantum algorithms optimized for specific problems. You need software stacks, compilers, debugging tools, an entire ecosystem that barely exists yet. But demonstrations matter. They shift the conversation from if to how, from maybe impossible to definitely hard but achievable. Something shifted recently, quietly in data published from a laboratory. The first genuine crossing of the error correction threshold. Not just reducing errors, but demonstrating that scaling up makes things better. The barrier broke. In late 2024, researchers at Google published results from a quantum processor called Willow. The paper was technical, dense with details about qubit calibration and error syndromes, but buried in the data was something extraordinary. For the first time, scaling up a quantum error correction system actually reduced errors instead of multiplying them. The technique they used is called a surface code, one of the most promising error correction schemes for superconducting qubits. The basic idea is geometric and almost elegant. Imagine a grid of physical qubits arranged in a checkerboard pattern. Some qubits, the data qubits, hold the actual quantum information you're trying to protect. Others, the measurement qubits, sit between them. By measuring these measurement qubits in specific patterns, you can detect errors without ever directly measuring the data qubits themselves. You're measuring properties of the error, not the information. The beauty is topological. You're encoding information not in individual qubits, but in global properties of the grid. Patterns that require multiple simultaneous errors to corrupt. Single errors disturb the pattern but don't destroy the information. You can detect them, correct them, and continue. Surface codes have favorable thresholds, around 1% error rate, which makes them achievable with current hardware, but they're expensive. Protecting a single logical qubit might require 100 or 1,000 physical qubits, depending on how much error suppression you need. The Willow experiment used a relatively small surface code, a grid of 49 physical qubits arranged into one logical qubit. Then they repeated the experiment with a larger surface code, 81 qubits, then 105 qubits. At each scale, they measured the error rate of the logical qubit. In previous experiments, everywhere in the world, adding more qubits made error rates worse. The additional complexity, additional control operations, additional opportunities for crosstalk and decoherence overwhelmed any potential benefit. You were building the leaky bucket. Willow's results showed the opposite. The 105 qubit surface code had lower error rates than the 81 qubit code, which had lower rates than the 49 qubit code. Not marginally lower, exponentially lower. Each doubling of the code size cut errors roughly in half. This is the signature of being below threshold. Error correction working as theoretically predicted, suppressing errors faster than they accumulate. The barrier crossed. Numbers can feel abstract, so let's make this concrete. What does below threshold actually mean in practice? A single physical qubit in the Willow chip has an error rate around 0.1% per operation. One error every 1,000 operations. That sounds impressive until you remember that useful quantum algorithms require millions or billions of operations. Errors accumulate. Without correction, the computation degrades into noise within microseconds. The 49 qubit surface code achieved a logical error rate of about 1 in 100,000 operations. Already a dramatic improvement. The error correction is working, but when they scaled up to the 105 qubit surface code, the logical error rate dropped to roughly 1 in 10 million operations. Read that again slowly. More qubits, fewer errors. The system is suppressing errors exponentially as it scales. This isn't just better engineering. This is crossing from one regime into another, from systems where noise dominates to systems where error correction dominates. It's the difference between sinking and floating. For years, researchers could demonstrate error correction in principle, show that it reduces errors compared to having no protection, but the best protected logical qubits still had higher error rates than doing nothing with fewer qubits. The overhead of error correction was too costly. Willow flipped this. The logical qubit, despite being built from 105 imperfect physical qubits, performs better than any individual physical qubit could, and crucially, the trajectory is right. Make the surface code bigger, and performance improves further. Extrapolate this trend, and you get to fault-tolerant quantum computing. Logical qubits so well protected that their error rates become negligible. Not perfect. Nothing in physics is perfect, but good enough to run arbitrarily long quantum algorithms without the computation collapsing into noise. The mathematics predicts this should be possible once you cross threshold. But mathematics and reality don't always agree. Thermodynamics, unanticipated noise sources, control imperfections, any of these could break the extrapolation. The fact that it's working in hardware, with real qubits in a real lab, shifts quantum computing from theoretical possibility to engineering challenge. An engineering challenge is solvable. Difficult, expensive, time-consuming, but solvable. Not blocked by physics, not limited by fundamental laws, just hard work ahead. There's a certain relief in that. a kind of permission to hope. Here's another way to understand what Willow achieved. Quantum memory lifetimes. A physical qubit in the Willow chip maintains coherence for about 100 microseconds. That's actually quite good for superconducting qubits. Years of engineering packed into that number, that 100 microseconds is barely enough time to perform a few dozen operations before decoherence erases everything. The surface code, by spreading information across many physical qubits and continuously detecting and correcting errors, extends this lifetime. The 105-qubit logical qubit maintained quantum information for up to 5 million microseconds, 5 seconds, in some experiments, from 100 microseconds to 5 seconds, a factor of 50,000 improvement. 5 seconds might not sound long. You're still reading this sentence 5 seconds after you started it. But in quantum computing, where operations happen in nanoseconds, 5 seconds is geological time. It's enough to perform millions of quantum gates, chain together complex algorithms, build computational structures that would be impossible otherwise. This is the first time any quantum memory has significantly outlived its physical components. The logical qubit isn't just protected, it's genuinely more robust than the pieces it's made from. The whole is healthier than the parts. There's something philosophically striking about this. Information preserved not by static storage, but by constant vigilance. Errors detected and corrected in real time. Healing happening faster than degradation. The logical qubit exists as a process, not an object. It's maintained the way a flame is maintained, or a living cell, through constant renewal and correction of entropy. Classical computers do this too, but we don't think about it much. Your laptop's memory has error correction running constantly in the background, fixing bit flips from cosmic rays and thermal noise. But that error correction is simple, local, invisible. Quantum error correction is all of those things made central, made load-bearing. The computation is error correction. You can't separate them. Every cycle, the system measures error syndromes, classically processes that information, decides on corrections, implements them. A feedback loop between quantum and classical happening thousands of times per second. It's a hybrid dance, neither purely quantum nor purely classical, but something new enabled by both working together, and it's working. The information persists. The quantum states survive long enough to be useful. That's what changed. That's the barrier breaking. Let's return to the question of why this felt impossible. It wasn't just difficulty. Physics is full of difficult things that are nonetheless achievable with enough effort. This felt like running into a law of nature, thermodynamics, measurement theory, the fundamental fragility of quantum states conspiring to make large-scale quantum computing impossible regardless of engineering. The second law of thermodynamics says entropy increases, disorder grows. Quantum coherence is a low entropy state, a delicate ordering imposed on a system that wants to thermalize, wants to equilibrate with its environment. Maintaining it requires fighting entropy, extracting heat, doing work. There are limits to how efficiently that can be done. Some physicists wondered if those thermodynamic limits might impose fundamental bounds on quantum computing. Measurement theory adds another layer. In quantum mechanics, measurement fundamentally disturbs the system. You can't observe a quantum state without changing it, but error correction requires continuous measurement, checking for errors without measuring the information itself. The distinction is subtle, possible in theory, but may be vulnerable to some deeper limitation we didn't understand. And complexity theory, the study of what's computable, had its own questions. Quantum computers are believed to be more powerful than classical computers for certain problems, but not arbitrarily powerful. They can't solve NP-complete problems in polynomial time probably. They're bounded by quantum complexity classes like BQP. Maybe those bounds reflect something about the physical realizability of quantum algorithms. Maybe the universe doesn't permit large-scale quantum computation, not because we can't build it, but because it would violate some deeper consistency of how information and physics relate. These concerns weren't crackpot theories. They came from serious physicists taking quantum mechanics and thermodynamics seriously, following the implications, asking hard questions about what nature actually allows. Crossing the error correction threshold doesn't invalidate those questions, but it shifts them. The universe is demonstrably permitting this. In a laboratory, in real hardware, quantum error correction is working at a scale where it suppresses errors faster than they accumulate. That doesn't mean it's easy to scale further. There might be new barriers at 1,000 qubits, or 10,000, or a million. The path from 105 qubits to the millions needed for useful applications is long and uncertain, but the fundamental barrier, the one that felt like a law of physics saying no, that one broke. What else are we wrong about? What other limits feel fundamental but might actually be contingent, might dissolve with the right technique, the right perspective, the right accumulation of patient effort? The universe is larger in possibility than our intuitions suggest. That's a lesson quantum mechanics teaches again and again. Classical intuition is parochial, local to our scale and experience. Reality accommodates more. Perhaps barriers are invitations, provocations to understand more deeply, to see what we're missing. Let's talk about what it actually took to achieve this. The engineering behind the impossibility. 105 qubits doesn't sound like many. Your laptop has billions of transistors, but each of those qubits must be controlled with extraordinary precision. Each quantum gate, the basic operations that manipulate qubit states, must be calibrated to better than 99.9% fidelity. Each measurement must distinguish quantum states without introducing decoherence. Each connection between qubits must be controllable, enabling entanglement when needed and isolation when not. Crosstalk is one of the hardest problems. When you manipulate one qubit, you inevitably disturb its neighbors slightly. Electromagnetic pulses don't have infinitely sharp boundaries. Qubits share components, cooling systems, control lines. Every operation on one qubit sends ripples through the system. Willow used sophisticated crosstalk cancellation, pre-computing the expected disturbances each operation would cause, and applying compensating pulses to other qubits. It's like noise-cancelling headphones for quantum states, generating anti-interference to maintain isolation. Calibration happens continuously. The properties of superconducting qubits drift over time, hours, minutes, sometimes seconds. Resonance frequencies shift, gate fidelities degrade. The control system must constantly recalibrate, measuring each qubit's current state and adjusting control parameters in real time. This is one place where classical computing power directly enables quantum computing. The classical computers controlling the quantum processor are running sophisticated optimization algorithms, machine learning models trained to find optimal control pulses, real-time processing of error syndromes to decide corrections. The quantum chip is tiny, a few square centimeters of silicon. The classical infrastructure supporting it fills rooms. Error syndrome detection is its own marvel. The surface code requires measuring specific combinations of qubits thousands of times per second to detect error patterns. Those measurements produce classical data, lots of it, that must be processed fast enough to implement corrections before decoherence destroys the information you're trying to protect. It's a race against time measured in microseconds. Detect error, process syndrome, compute correction, apply correction, all in less time than it takes the quantum state to decohere. Classical algorithms have been optimized to nanosecond precision to win this race, and somehow, improbably, it works. The error correction keeps pace with decoherence. The logical qubit survives. The computation proceeds. There's something humbling about the scale of effort required. Decades of research, hundreds of researchers, millions of hours of work, extraordinary expense, all to make 105 atoms in a silicon chip behave quantum mechanically for 5 seconds. And yet, 5 seconds is enough. Enough to cross the threshold. Enough to demonstrate that the path forward exists. Patience and precision compounded over time, that's how barriers break. It would be easy to declare victory here, to say quantum computing is solved and the future has arrived, but that would be premature. What Willow demonstrated is profound, genuine error correction working below threshold, scaling in the right direction. But the scale is still tiny. One logical qubit built from 105 physical qubits. Useful quantum algorithms will require thousands or millions of logical qubits, each built from hundreds of physical qubits. We're talking about systems with billions of well-controlled quantum elements. Current labs have dozens of qubits. The best systems have a few hundred. Getting to millions requires not just incremental scaling, but architectural changes. New ways to connect qubits across chips, across dilution refrigerators, perhaps across rooms, quantum networking to link distributed quantum processors, control electronics that can manage millions of calibration parameters simultaneously. Connectivity is particularly challenging. In a surface code, qubits only need to interact with their nearest neighbors on the grid. But quantum algorithms often require long-range entanglement, qubits on opposite sides of the chip interacting. Creating that connectivity without introducing crosstalk or sacrificing gate fidelity is an open problem. Gate fidelity requirements will likely tighten as systems scale. The threshold theorem assumes certain error models, independent random errors at known rates. Real systems have correlated errors, systematic biases, noise sources that don't match the mathematical assumptions. As systems grow, maintaining the error model fidelity requires even better isolation and control. And then there's the software stack. We barely know how to program quantum computers. Quantum algorithms exist in research papers, elegant in abstract, but translating them into efficient sequences of gates on real hardware with real constraints is as much art as science. Compilers, optimizers, debugging tools, the entire ecosystem of software development that makes classical computers useful mostly doesn't exist yet for quantum systems. So the breakthrough is real, but it's a beginning, not an ending. A demonstration of principle that shifts the goalpost from maybe impossible to definitely achievable with enormous effort. How long until useful quantum computers? Estimates range from 5 years to 50, depending on who you ask and what counts as useful. The honest answer is uncertainty. Engineering timelines are notoriously hard to predict, especially for technologies that don't exist yet. But the trajectory has changed. There's a path forward now, visible in the data. More qubits reduce errors. Logical qubits outperform physical qubits. Error correction works. The door is open. What lies beyond it remains to be discovered. Let's step back and think about what quantum computers actually do, how they compute in ways fundamentally different from anything classical. A classical computer, at its heart, is a machine that manipulates bits. Each bit is either 0 or 1, definitively, at every moment. Computation proceeds step by step, each operation transforming the bits according to logical rules. If you want to try multiple possibilities, like testing different solutions to a problem, you have to try them sequentially, one after another. More possibilities mean more time. This is true even for parallel classical computers. You can divide the work across multiple processors, but each processor is still evaluating possibilities sequentially. You're working faster by working in parallel, but you're still exploring the solution space one path at a time, just with multiple explorers. Quantum computers don't work like this at all. A qubit in superposition isn't secretly 0 or 1, it's genuinely both, simultaneously, until measured. And when you have multiple qubits entangled together, the system exists in a superposition of all possible combinations of those qubits. 2 qubits can be in 4 states simultaneously, 3 qubits, 8 states, 10 qubits, 1024 states. The number of simultaneous states grows exponentially with the number of qubits. 50 qubits can be in a superposition of about 1 quadrillion states simultaneously. That's more states than there are stars in the Milky Way, all existing at once in a system you could hold in your hand. If it weren't so cold, it would instantly destroy your hand. A quantum algorithm doesn't evaluate these states one by one. It manipulates the entire superposition at once. A single quantum gate operation affects all the possible states simultaneously. The computation explores the entire solution space in parallel, not parallel in the sense of multiple processors, but parallel in the sense of quantum superposition, existing in many configurations at once. Of course, there's a catch. When you measure the qubits to read out the result, the superposition collapses. You get one answer, a specific sequence of zeros and ones, all that exponential parallelism, and you only get to see one outcome. The art of quantum algorithm design is setting up the superposition and manipulating it so that when it collapses, it's likely to collapse to the right answer. You're choreographing interference patterns in probability space, arranging things so that wrong answers destructively interfere and cancel out, while right answers constructively interfere and amplify. It's less like searching through possibilities and more like tuning a quantum system to naturally settle into the solution state. You're not computing an answer, you're creating conditions where reality computes the answer for you. Measurement is the final step, collapsing the superposition and extracting classical information from quantum probability. What you measure is a sample from the probability distribution the quantum algorithm created. For well-designed algorithms, that sample is the solution you are seeking. This is computation as fundamentally different from classical as classical is from mechanical. Not just faster, different in kind. Not all problems benefit from quantum computation. Some problems are inherently sequential, requiring step-by-step logic that doesn't benefit from superposition, but certain classes of problems, combinatorial optimization, searching through possibilities, simulating quantum systems, align beautifully with quantum computing's strengths. Consider the traveling salesman problem. Given a list of cities and distances between them, find the shortest route that visits each city exactly once. With 5 cities, there are 12 possible routes. With 10 cities, over 180,000 routes. With 20 cities, about 1018 routes. With 50 cities, more possible routes than there are atoms in the observable universe. Classical computers face exponential scaling. Double the number of cities, and the number of routes increases exponentially. At some point, even the fastest supercomputer can't check every route before the heat death of the universe. Quantum algorithms don't solve this by checking every route faster. They restructure the problem entirely. Algorithms like quantum annealing or variational quantum eigensolvers set up the problem as an energy landscape, where each possible solution corresponds to a state with some energy. The lowest energy state is the best solution. The quantum system naturally explores this landscape through quantum tunneling and superposition, potentially settling into low-energy states much faster than classical search. Grover's algorithm offers provable speedup for unstructured search. Searching through n items classically requires checking, on average, n2 items. Grover's algorithm finds the item in roughly root n operations. For 1 million items, that's the difference between 500,000 operations and 1,000. Not exponential speedup, but quadratic, significant for large searches. Shor's algorithm is more dramatic. Factoring a large number into primes is exponentially hard for classical computers, the basis of modern encryption. Shor's algorithm can factor in polynomial time, a number that would take classical computers millions of years to factor, could potentially be factored by a quantum computer in hours. This doesn't mean quantum computers can solve NP-complete problems efficiently. Probably not. They're not magic. They're bounded by complexity classes, just different ones than classical computers. But within their complexity class, they offer exponential speedup for specific problem types. The catch is that most of these algorithms require fault-tolerant quantum computers with thousands or millions of qubits. We're not there yet. Current quantum computers can run small versions of these algorithms as demonstrations, but not at scales that outperform classical computers on practical problems, except for one thing: quantum simulation. Simulating quantum systems is exponentially hard for classical computers because describing the quantum state requires exponentially many parameters. But quantum computers don't need to describe quantum states. They are quantum states. Simulating a molecule on a quantum computer means creating analogous quantum states in your qubits and letting them evolve. The simulation is direct, not approximate. This might be the first killer application, designing molecules, materials, and drugs by simulating their quantum mechanical behavior directly. Classical computers can't do this efficiently. Quantum computers can. The question shifts from what can quantum computers do to what problems are we currently avoiding because they're too hard classically, but become tractable quantum mechanically. The answer might surprise us. History suggests that genuinely new computational capabilities enable applications their inventors never imagined. There's something philosophically elegant about using quantum systems to simulate other quantum systems. It feels right, natural, like the universe understanding itself through self-similarity. Classical computers simulate quantum systems by tracking numbers, amplitudes, probabilities, wave functions. For a single particle, this is manageable. But quantum systems entangle. Two particles together aren't just twice as complex. Their joint quantum state has more dimensions. Three particles, more dimensions still. The number of parameters needed to describe a quantum system grows exponentially with the number of particles. 10 electrons require tracking about 60,000 numbers. 20 electrons, about 4 billion numbers. 30 electrons, more numbers than atoms in your body, somewhere around 300 particles. You need more numbers to describe the quantum state than there are atoms in the observable universe. Classical computers hit a wall. Not a practical wall that better hardware can overcome, but an information-theoretic wall. The universe doesn't contain enough matter to represent the quantum state classically, and yet the universe clearly simulates these systems. Chemistry happens, molecules form, photosynthesis works. Your neurons are firing right now through quantum mechanical processes involving millions of electrons. Reality computes these interactions efficiently using quantum mechanics itself. Richard Feynman noticed this in the 1980s, the first clear articulation of why quantum computers should exist. If you want to simulate quantum systems, use quantum systems. Don't try to describe them classically. Create analogous quantum states in a controllable system and let physics do the simulation. Consider a drug molecule binding to a protein. The binding involves quantum mechanical interactions, electron orbitals overlapping, bonds forming, energy states shifting. Understanding this precisely could predict drug effectiveness, side effects, optimal molecular shapes. Classical computers use approximations, density functional theory, molecular dynamics, sophisticated techniques that work well for simple molecules, but struggle with complex pharmaceuticals. The approximations introduce errors. You can improve them with more computation, but you're fighting exponential scaling. A quantum computer could simulate the molecule and protein directly, map their quantum states onto qubits, let the qubits evolve according to the same quantum mechanical rules that govern the real molecules. Measure the result. The simulation is the thing itself, just in a different physical substrate. Not an approximation, not a model, a direct quantum mechanical analog. This applies to materials science, catalysis, superconductivity, photosynthesis, and any process where quantum effects dominate. The problems we've been solving approximately because exact simulation is impossible, those become tractable. Or consider high-temperature superconductors. They work, we have them, we use them, but we don't fully understand why they work. The quantum mechanical interactions of electrons in these materials are too complex for classical simulation. If we understood them better, we might design room-temperature superconductors, materials that revolutionize energy transmission, computing, transportation. Quantum simulation could map those electron interactions directly, explore different crystal structures, find the mechanisms we're missing. Reality simulating itself. The universe as both the computer and the program, both the question and the answer. There's something deeply satisfying about this. It suggests that the right tools for understanding nature might be built from nature's own mechanics, not abstracted away into classical approximation. And with error correction working, with logical qubits outliving physical ones, these simulations become more than theoretical possibilities. They become engineering goals. Let's turn to something less comfortable. Quantum computers as threats. Most encryption securing the internet relies on mathematical problems that are hard for classical computers. RSA encryption, for example, depends on the difficulty of factoring large numbers. Given a 2048-bit number that's the product of two primes, finding those primes takes classical computers an impractically long time. Longer than the age of the universe for sufficiently large numbers. This asymmetry, easy to multiply primes, hard to factor the product, enables public key cryptography. You can publish an encryption key derived from the product, without worrying that someone will factor it to find your private decryption key. The mathematics protects you until someone builds a quantum computer running Shor's algorithm. Shor's algorithm, proven in 1994, can factor large numbers in polynomial time. A quantum computer with a few thousand logical qubits could factor 2048-bit numbers in hours or days. Every message encrypted with RSA, every secure transaction, every digital signature potentially vulnerable. This isn't speculation. The mathematics is proven. The only uncertainty is timeline. How long until quantum computers are large enough and reliable enough to run Shor's algorithm on real keys? Estimates vary, but prudent organizations are migrating to post-quantum cryptography now. The National Institute of Standards and Technology has standardized new encryption algorithms designed to resist quantum attacks based on mathematical problems believed to be hard even for quantum computers: lattice-based cryptography, code-based cryptography, multivariate polynomial cryptography, believed to be hard. We don't have proofs. It's possible that future quantum algorithms will break these too. Cryptography is always a race. New locks, new lockpicks, new locks. There's also a darker timeline concern. Harvest now, decrypt later. Adversaries with sufficient resources could record encrypted communications today and store them, waiting for quantum computers capable of breaking the encryption years from now. If your encrypted messages contain information valuable in the future, they're potentially compromised even if current encryption is unbreakable. This has already changed policy. Governments classify some information not just by sensitivity, but by how long it must remain secret. Information that must stay secret for decades requires post-quantum encryption now, even though quantum computers don't exist yet. Blockchain and cryptocurrency add another layer. Many cryptocurrencies rely on elliptic curve cryptography, also vulnerable to quantum attacks. Some are exploring quantum-resistant alternatives. Others argue that by the time quantum computers threaten blockchain, the technology will have evolved beyond recognition anyway. The interesting philosophical question is whether this represents quantum computers being destructive, or just revealing that our notion of secure was always temporary, contingent on classical computational limits that were never fundamental. Barriers falling in encryption, just like barriers falling in quantum error correction. The universe doesn't care about human categories of construction versus destruction. It permits what physics permits and prohibits what physics prohibits. Our tools shape what's possible, including what's possible for those who don't share our interests. History teaches humility about predicting technological applications. Early computers were imagined as calculating machines, tools for mathematicians, artillery tables, scientific computation. The idea that they'd become communication devices, entertainment platforms, global information networks, this wasn't even conceivable in the 1950s. The applications that define computing today didn't exist in the minds of computing's pioneers. The internet was designed for resilient military communication and academic resource sharing. Social media, streaming video, instant global connection, unforeseen. The technology enabled the applications, and the applications transformed society in ways the technology's creators never imagined. Quantum computers are early in this cycle. We have theoretical algorithms and speculative applications, but we don't know what will actually matter. What uses will emerge that we can't currently imagine because we're still thinking classically, still trying to map quantum computing onto problems we already understand. Quantum machine learning is one frontier. Classical neural networks have revolutionized AI by learning patterns in data through optimization. Quantum neural networks could process quantum data, information encoded in superposition and entanglement, in ways classical networks can't represent. What patterns exist in quantum data? What could we learn if we looked? Quantum sensing uses quantum states to measure with precision beyond classical limits. Gravitational wave detectors, magnetic field sensors, atomic clocks all benefit from quantum techniques. Could quantum computers enhance this, processing quantum sensor data to extract information classical computers miss? Financial modeling involves simulating markets, pricing complex derivatives, managing risk across correlated assets. These are optimization problems with quantum approaches. but also probabilistic systems where quantum probability might offer native advantages. What if markets themselves exhibit quantum-like correlations we can't currently detect because our analysis tools are classical? Climate modeling requires simulating coupled and nonlinear systems, atmosphere, oceans, ice, biosphere, at resolutions fine enough to capture emergent phenomena. Could quantum simulation accelerate this, making long-term climate prediction more accurate, or reveal dynamics we're currently averaging over? Drug discovery is often mentioned, but what about personalized medicine? Simulating how specific molecular variations in your genome affect drug metabolism at quantum mechanical precision, medicine tailored not to populations but to individuals, designed by quantum simulation. And there are wild possibilities. Quantum artificial intelligence that thinks in superposition, exploring cognitive strategies unavailable to classical systems. Quantum creativity, if such a thing makes sense. Quantum economics modeling agent-based systems where decisions exist in superposition until measured by transaction. Some of these will prove impossible, impractical, or unnecessary, but some might transform fields we can't anticipate. The gap between what we can imagine and what becomes possible is where genuine novelty lives. The barrier breaking and error correction doesn't just make existing applications more achievable, it opens space for applications we haven't thought of yet. Waiting in the possibility space quantum computers will explore. Quantum computers force us to confront something strange about reality. We're building powerful technology from phenomena we don't fully understand philosophically. The measurement problem, what happens when a quantum system is observed, remains one of physics' deepest unresolved questions. Quantum mechanics tells us how to calculate probabilities, how to predict measurement outcomes with extraordinary precision, but it doesn't tell us what measurement is or why observation collapses superposition into definite states. Multiple interpretations exist, mathematically equivalent but philosophically incompatible. The Copenhagen interpretation says quantum systems don't have definite properties until measured. The wave function describes not reality but our knowledge. Measurement creates reality at quantum scales. This works pragmatically, but leaves consciousness and observation undefined. Does a detector count as an observer? Does it require awareness? The many worlds interpretation says superpositions never collapse. Every quantum possibility occurs, but in different branches of reality. When you measure a qubit, the universe splits. One version of you sees 0, another sees 1, both real, both continuing. Measurement doesn't collapse possibility but divides observers across branches. Elegantly removes the measurement problem by making everything deterministic across all branches, but at the cost of infinite unobservable universes. Objective collapse theories propose that superpositions spontaneously collapse due to gravity or other physical mechanisms, no observer needed. Measurement just amplifies quantum randomness to macroscopic scales, still speculative, testable in principle but not yet tested. Quantum Bayesianism cubism treats quantum states as personal beliefs, updated by observation. Wave functions describe an agent's knowledge, not objective reality. Measurement is learning, not physical collapse. Resolves measurement problem by making it subjective but raises questions about whether there's any objective reality beneath our observations. And quantum computers? They work in all interpretations. The mathematics is identical. Whether superpositions are real, or knowledge states, or branches of splitting universes, the computer doesn't care. It manipulates quantum states according to rules that work, producing results that match observation. We're building technology on metaphysically uncertain ground, flying before understanding flight at philosophical depth. And that's okay. Engineering often outruns theory, but there's something humbling about it. The universe permits us to use quantum mechanics without requiring us to understand it. Maybe understanding comes later, guided by the technologies we build. Maybe some questions remain unanswerable, and we learn to live with functioning mysteries. Quantum computing might ultimately teach us more about quantum mechanics than quantum mechanics taught us about quantum computing. There's a perspective growing in physics that information is fundamental, more fundamental than matter or energy. John Wheeler's It from Bit suggests reality arises from information. Every physical object, every particle, every interaction, all ultimately reducible to binary questions answered by observation. Matter and energy are what information looks like when instantiated in physics. Quantum information theory extends this. Quantum bits are more fundamental than classical bits because they're what the universe uses natively. Classical information emerges when quantum information is measured, collapsed, averaged. If this is true, if information is fundamental, then quantum mechanics isn't a description of reality, but reality's programming language. Wave functions aren't calculating what particles do, they are what particles do. Superposition isn't particles being uncertain, but particles being information that hasn't been compiled into classical definiteness yet. This reframes quantum computers dramatically. We're not building artificial devices that happen to use quantum mechanics. We're creating controlled subsystems where the universe's natural computation becomes visible and manipulatable. The universe is always computing. That's what physical evolution is, solving the Schrödinger equation moment by moment. Quantum computers just give us some steering over what it computes. Consider, when a molecule binds to a receptor, quantum mechanical interactions determine the outcome. The universe computes the binding energy, the configuration, the result, not by calculating but by being. Physical evolution is computation. When we simulate that molecule on a quantum computer, we're not approximating the universe's computation. We're creating a parallel instance of it in a different physical system. The quantum computer and the actual molecule are both the universe computing similar quantum mechanical processes. This suggests something strange. The universe might be, in some sense, a quantum computer computing itself. Not designed, not purposeful, just the fact that physical laws applied to quantum states produce evolution that looks indistinguishable from computation. What's the universe computing? Itself, its own next state. Every moment, the wave function of the entire universe evolves according to quantum mechanics, producing the next moment. That's the computation. Input, current state, output, next state, repeated at the Planck timescale, about 1044 times per second. Quantum computers let us peek at that computation, redirect small portions of it, read out results. We're not creating something separate from nature. We're coaxing nature to compute specific things we care about instead of random thermal noise. If this perspective is right, then consciousness, thought, creativity, all might be quantum computations happening in the warm, noisy classical limit, where decoherence is rapid and quantum effects are subtle. We're quantum systems that happen to maintain enough coherence to think, at least briefly, a universe computing itself, becoming aware of itself in localized pockets of complexity, building tools to compute more deliberately, strange loops all the way down. Quantum mechanics introduces randomness at the foundation of reality. Or does it? Radioactive decay is genuinely random. Given a single unstable atom, quantum mechanics predicts the probability it will decay in the next second, but not whether it actually will. That outcome is fundamentally probabilistic, not because we lack information. There's no hidden variable determining when decay happens. It just happens, randomly, when the wave function collapses. Einstein hated this. God does not play dice with the universe, he famously objected. The idea that reality is fundamentally probabilistic, that identical systems can produce different outcomes for no reason beyond quantum randomness, felt incomplete to him. He suspected hidden variables, information we couldn't access but that existed, making the randomness only apparent. Bell's theorem, proven in 1964, showed Einstein was wrong, not by assertion but by mathematics. If hidden variables exist, certain statistical correlations in entangled particles must obey specific limits. Experiments violate those limits. Quantum randomness isn't ignorance, it's fundamental. The universe actually does play dice. Or more precisely, the universe is made of dice that have no value until rolled, that exist in superposition of all faces simultaneously until observation forces them to choose. Quantum computers exploit this. Quantum algorithms use superposition and interference to structure probability distributions, making desired outcomes more likely and undesired ones less likely. but there's always randomness. Run a quantum algorithm twice with identical input, and you might get different answers, not because the algorithm is flawed, but because measurement samples from a probability distribution. For some applications, this is fine. Run the algorithm many times. The right answer appears most frequently. Wrong answers are rare. Statistical confidence builds, but it raises a philosophical question. If computation involves irreducible randomness, what does the answer even mean? Is there an objective truth the algorithm finds, or only probability distributions over outcomes? And what about creativity, novelty, free will, concepts that seem to require something beyond deterministic cause and effect? In a classical universe, everything is determined by initial conditions and physical laws. The future is already written, just not yet played out. Free will becomes illusion, creativity mere recombination of inputs. Quantum randomness might provide space for genuine novelty. If decisions involve quantum measurements, neurons firing triggered by ion channels where quantum tunneling matters, then outcomes aren't fully determined by the past. There's room for true randomness, and perhaps in that randomness freedom, or perhaps not. Randomness isn't choice, a coin flip isn't free will, but maybe it's a component, combined with complex feedback loops in brains, producing emergent behavior we experience as agency. Quantum computers don't answer these questions, they make them sharper, more urgent. We're building machines that think probabilistically. If they become intelligent, creative, autonomous, what will that say about our own minds? Physics isn't just about what exists, it's about what can be known, what can be computed, what information is even accessible in principle. Heisenberg's uncertainty principle. You can't simultaneously know a particle's exact position and exact momentum, not because your measurement tools are imperfect, but because the particle doesn't have both definite values simultaneously. The more precisely you determine one, the less defined the other becomes. It's not a limitation of knowledge, it's a limitation of reality itself. The no-cloning theorem. You can't make a perfect copy of an unknown quantum state. This isn't engineering difficulty, it's proven impossible by the linearity of quantum mechanics. Information can be moved, transformed, entangled, but not duplicated. This limits error correction, communication, computation in fundamental ways. The holographic principle suggests the universe might have a maximum information density. A region of space can only contain so much information, bounded by its surface area, not its volume. More information than that, and it collapses into a black hole. This implies computation itself is limited. You can't pack infinite processing into finite space, no matter how clever your engineering. Computational complexity classes might reflect these physical limits. P versus NP, whether problems with quickly verifiable solutions also have quickly findable solutions, feels like a mathematical question. But maybe it's physical. Maybe the structure of reality forbids certain types of efficient computation, and our mathematical complexity classes are discovering those boundaries. Quantum computers expand what's computable but don't eliminate limits. BQP, the class of problems quantum computers can solve efficiently, is larger than P but probably smaller than NP. Some problems remain hard even for quantum systems. The universe seems to protect certain kinds of difficulty. Why? Maybe because if everything were easily computable, reality would collapse into triviality. The interesting structure of the universe, the emergence of complexity, life, consciousness, might require that some things stay hard. Easy answers everywhere would mean no novelty, no exploration, no discovery. Gödel's incompleteness theorems add another layer. In any sufficiently complex logical system, there are true statements that can't be proven within that system. Mathematics contains truths beyond reach of its own axioms. If the universe is fundamentally mathematical, if physical laws are logical structures, does incompleteness apply to reality? Are there facts about the universe that can't be determined by observation or experiment, not because we lack tools, but because they're undecidable even in principle? Quantum computers, powerful as they might become, can't escape these limits. They're bound by quantum mechanics, which is bound by logic, which is bound by Gödel. Expanding computational power reveals deeper layers of unknowability. Perhaps the universe is structured such that perfect knowledge is impossible, ensuring there's always something left to wonder about. Barriers that keep us curious. Quantum entanglement is often called the strangest feature of quantum mechanics, stranger even than superposition, and quantum computing relies on it essentially. When two particles are entangled, measuring one instantly affects the other, regardless of distance, not because information travels between them, but because they don't have separate quantum states anymore. They're one system, described by a single wave function spanning space. Einstein called this spooky action at a distance and saw it as evidence that quantum mechanics was incomplete. How could particles light years apart be instantaneously connected? It violated his intuition about locality, the idea that objects are only influenced by their immediate surroundings. Bell's theorem proved Einstein's intuition wrong. Entangled particles really do exhibit correlations that can't be explained by any local hidden variable theory. The connection is real, non-local, instantaneous, but it's subtle. You can't use entanglement to send messages faster than light. Measuring one particle gives a random result. The correlation only appears when you compare measurements on both particles. Information still travels classically, at light speed or below. Causality is safe, yet the connection exists. Two entangled qubits, separated by any distance, remain one quantum system. In quantum computing, this enables operations that affect multiple qubits simultaneously, creating correlations classical systems can't replicate. Distributed quantum computing could use entanglement to link quantum processors, creating networks where quantum information flows between nodes, a quantum internet where entanglement provides the connection, enabling applications like secure communication, distributed quantum computation, networked quantum sensing. Philosophically, entanglement suggests that separation might be less fundamental than it appears. At quantum scales, parts of the universe can be more connected than their spatial separation suggests. Locality emerges at classical scales, but underneath, reality is webbed with non-local correlations. This resonates metaphorically with human experience. We feel separate, bounded by skin, isolated in individual minds, but we're entangled socially, culturally, historically. Actions ripple across networks of connection, affecting people we'll never meet. Information, ideas, influence flow non-locally through communication. The metaphor isn't perfect. Quantum entanglement is specific, technical, not mystical. But there's something compelling about the universe having built-in connection at its foundations, separateness as emergent, connection as fundamental. Quantum computers make this practical, functional. Entanglement isn't just spooky, it's a resource, something to create, maintain, manipulate for computation. Perhaps as quantum technologies mature, we'll develop intuitions about entanglement the way we have intuitions about classical mechanics. It'll stop feeling strange and start feeling like how things obviously are. Or perhaps it'll remain strange, a perpetual reminder that reality exceeds our evolved capacity to grasp it fully. Either way, the connections are real. The universe permits them, and we're learning to use them. Ask 10 quantum computing researchers when fault-tolerant quantum computers will exist, and you'll get 10 different answers, ranging from 5 years to 50, sometimes with the caveat or never. The optimists point to exponential progress. Error rates have dropped dramatically. Qubit counts have grown. Coherence times have extended. The threshold is crossed. With sufficient investment and engineering effort, scaling to millions of qubits is solvable, hard, but not impossible. The pessimists note that every technology faces unanticipated barriers at scale. What works for 100 qubits might not work for 10,000. New noise sources might emerge, control complexity might become unmanageable. The path from laboratory demonstration to industrial reliability is long and often surprising. Historical analogies offer both hope and caution. Classical computing followed exponential growth, Moore's law doubling transistor counts every 2 years for decades. From room-sized computers to smartphones in a human lifetime, if quantum computing follows similar exponentials, useful systems could arrive faster than expected, but fusion power has been 30 years away for 60 years. Technical challenges that looked solvable in principle turned out to compound in practice. Plasma instabilities, materials degradation, economic viability, each solved problem revealed new ones. Maybe quantum computing has its own plasma instabilities waiting at larger scales. The difference might be that quantum computing already works at small scales. Fusion works in stars and bombs, but not controllably for power generation. Quantum computers are already computing, already crossing error correction thresholds, already demonstrating principles. It's scaling, not fundamental physics, that remains. Timelines also depend on what counts as useful. A quantum computer that simulates specific molecules better than classical approaches might arrive soon, perhaps within a decade. A quantum computer that breaks RSA encryption requires more qubits, better connectivity, maybe 2 decades. A general-purpose quantum computer you can program for arbitrary problems, harder to predict, and timelines assume steady progress. But technology doesn't advance smoothly. Breakthroughs cluster unpredictably. Willow's error correction success might accelerate other groups' efforts, or it might reveal new challenges no one anticipated. Predicting the timing of innovations is notoriously unreliable. The honest position is uncertainty. We know more than we did. The barrier broke, the path exists, but we don't know what lies along that path, what new barriers wait, what unexpected advantages might accelerate progress. Embracing uncertainty isn't pessimism, it's realism. The future is genuinely open, shaped by decisions not yet made, discoveries not yet realized, problems not yet encountered, and in that openness, possibility lives. Quantum computers probably won't replace classical computers. They'll complement them, each handling tasks suited to their strengths. Most computation is classical. Word processing, web browsing, video streaming, database queries, none of these benefit from quantum mechanics. Classical computers are excellent at sequential logic, data storage, interface management. They're cheap, reliable, well understood, and continuously improving. Quantum computers excel at specific problems, simulating quantum systems, certain optimization problems, searching specific structures, breaking particular encryption schemes, narrow domains where quantum mechanics provides exponential advantage. The likely future is hybrid. Classical computers handling most tasks, calling quantum coprocessors for specific bottlenecks. Like how modern computers use specialized hardware, GPUs for graphics, TPUs for machine learning, FPGAs for specific signal processing. Variational quantum algorithms already work this way. A classical optimizer proposes parameters. The quantum computer evaluates them and returns a measurement. The classical optimizer adjusts and iterates. The quantum system is an oracle, consulted for specific questions it can answer efficiently. Quantum machine learning might follow similar patterns. Classical neural networks process most data, but quantum subroutines handle specific computations, perhaps quantum data that can't be efficiently represented classically, or optimization landscapes where quantum exploration offers advantage. Chemistry simulations could use quantum processors for electron interactions, the quantum mechanical core, while classical computers handle molecular dynamics, solvent effects, thermal averaging. Each system doing what it does best, results combined. This hybrid approach has practical advantages. You don't need to rebuild all of computing from quantum scratch. You integrate quantum modules into existing workflows, adding capability without replacing infrastructure. It also acknowledges that most problems don't need quantum solutions. The world isn't bottlenecked on factoring large numbers or simulating molecules. But for the problems where quantum advantage exists, access to quantum coprocessors could be transformative. Cloud quantum computing is already emerging. Companies offering quantum processors, accessible via internet, where you submit quantum circuits and receive results. You don't need a dilution refrigerator in your office, just API access to someone else's quantum hardware. This democratizes access but raises new questions about security, verification, and trust. How do you know the quantum computer actually ran your computation correctly? How do you protect proprietary algorithms or sensitive data sent to remote quantum processors? Post-quantum cryptography becomes essential in this hybrid future. Classical encryption protects data in transit. Quantum coprocessors process it. Results return encrypted. The entire pipeline must resist quantum attacks. Even as quantum computers become more capable, the transition won't be sudden. No day when quantum computers replace classical ones. Instead, gradual integration, expanding from specialized research to niche applications to broader availability, like how GPUs evolved from specialized graphics hardware to general-purpose accelerators used in machine learning, scientific computing, and cryptocurrency mining. Different computational paradigms coexisting, cooperating, each finding roles that match their capabilities. Cryptography is about to undergo its biggest transition since public key encryption was invented in the 1970s. Current encryption assumes factoring large numbers is hard. This assumption has held for decades, protecting everything from banking to messaging to state secrets. But it's contingent, dependent on classical computers' limitations. Quantum computers dissolve that contingency. Shor's algorithm proves that factoring becomes efficient on quantum systems. The timeline is uncertain, but the vulnerability is mathematically certain. Eventually, quantum computers will break RSA, Diffie-Hellman, elliptic curve cryptography, the foundations of internet security. Migration is already underway. NIST's post-quantum cryptography standards were finalized in 2024, providing encryption algorithms believed resistant to quantum attacks. Based on lattice problems, code-based cryptography, hash functions, mathematics that seems hard even for quantum computers. Seems hard is uncomfortable. Unlike RSA security, which reduces to a well-studied number theory problem, post-quantum algorithms are newer, less tested. We don't have proofs they're quantum resistant, only evidence that current quantum algorithms don't break them. Future discoveries might change this, but waiting isn't safe either. Harvest now, decrypt later attacks are already happening. Adversaries recording encrypted data now, storing it encrypted, waiting for quantum computers capable of breaking it years from now. If your secrets must stay secret for decades, you need post-quantum encryption now. This creates strange timeline pressures. Data encrypted today might be vulnerable 10 years from now, even though quantum computers don't exist yet. Long-term security requires anticipating future capabilities. Blockchain and cryptocurrency add complexity. Many cryptocurrencies use elliptic curve signatures vulnerable to quantum attacks. Some are exploring quantum-resistant alternatives. Others argue the technology will evolve before quantum threats materialize, but the possibility of a quantum computer suddenly compromising billions in digital assets creates existential questions for cryptocurrency. What happens to trust when encryption barriers fall? If secure communication becomes insecure retroactively, what conversations were compromised? What secrets were never secret, just temporarily protected? There's also potential for new cryptography enabled by quantum mechanics. Quantum key distribution uses entanglement to create encryption keys with provable security. Any eavesdropping disturbs the quantum states, revealing the intrusion. Physics guarantees security, not just mathematical difficulty. These systems exist in research labs and a few high-security applications. Whether they scale to general use depends on engineering challenges around quantum networking, error rates, and practical deployment. The philosophical shift is from security through computational difficulty to security through physical law. Instead of hoping problems stay hard, you use quantum mechanics to make eavesdropping physically detectable. One kind of barrier falls, classical encryption's protection. Another potentially rises, quantum mechanics' fundamental constraints on observation. The universe remains neutral, permitting both. Materials science is limited by search space. There are more possible molecular arrangements than we can explore experimentally. Consider a simple organic molecule with 30 atoms. The number of ways to arrange those atoms into valid molecules is astronomical. Testing each one experimentally, synthesizing it, measuring properties, checking stability, would take millennia. Classical simulation helps but hits exponential scaling. Quantum mechanical interactions determine material properties, conductivity, magnetism, catalytic activity, strength. Simulating these accurately requires quantum calculations that become intractable for complex materials. This leaves enormous possibility space unexplored. Somewhere in that space might be room temperature superconductors, materials conducting electricity without resistance at practical temperatures, or catalysts that capture carbon dioxide efficiently, or solar cells approaching theoretical efficiency limits, or batteries with 10 times current energy density. We can't find them because we can't search efficiently. We're exploring mostly randomly, guided by chemical intuition and incremental modification of known materials. Quantum computers could change this. Simulate candidate materials at quantum mechanical accuracy, predict properties before synthesis, explore possibility space systematically rather than randomly. The pharmaceutical industry faces similar challenges. Billions of possible drug-like molecules, only tiny fractions tested. Drug discovery is expensive partly because most candidates fail. They don't bind to target proteins, or they bind but have side effects, or they work in vitro but not in vivo. Most investment is wasted on dead ends. Quantum simulation of molecular interactions could filter candidates computationally, testing millions of molecules in silico before synthesizing the most promising, reducing failed experiments, accelerating timelines, lowering costs. Enzyme design is another frontier. Enzymes are biological catalysts, proteins that accelerate chemical reactions with extraordinary specificity. We use natural enzymes in industry, but they evolved for biology, not manufacturing. Designing custom enzymes for specific industrial reactions could enable cleaner processes, lower energy requirements, less waste. But protein folding, predicting how amino acid sequences fold into three-dimensional structures, is quantum mechanically complex. And understanding how folded proteins interact with substrates requires simulating quantum effects in enzyme active sites. Quantum computers could design enzymes computationally, exploring sequence space to find proteins that fold correctly and catalyze desired reactions. Engineering biology at molecular precision, the materials that don't exist yet, might solve problems we currently consider intractable. Carbon capture at scale, energy storage for renewable grids, biodegradable plastics with properties matching current materials, drought-resistant crops engineered at molecular level. The possibility space is vast. We're currently exploring a tiny biased sample, materials close to ones we already know. Quantum simulation could venture further, finding solutions evolution and human intuition never discovered. Not guarantees. Simulation still requires knowing what properties you want and having algorithms that efficiently search. But the barrier of quantum mechanical simulation cost drops, opening space previously inaccessible. Every new capability changes not just what we can answer, but what we can ask. Before telescopes, questions about planetary motion were limited to naked eye observation. Telescopes revealed moons orbiting Jupiter, phases of Venus, Saturn's rings, phenomena that sharpened questions about gravity, celestial mechanics, the structure of the solar system. Before particle accelerators, questions about atomic structure were theoretical. Accelerators revealed quarks, gluons, the Higgs boson, data that refined questions about fundamental forces, symmetries, the origin of mass. Quantum computers might similarly sharpen questions about physics itself. Quantum gravity, the unification of quantum mechanics and general relativity, remains unsolved. Neither theory fits cleanly with the other. Could quantum computers simulate conditions where both matter, exploring regimes we can't access experimentally, simulate quantum fields in curved spacetime, look for signatures of quantum gravity effects? Dark matter and dark energy comprise 95% of the universe's mass energy, but we don't know what they are. Could quantum simulations of exotic particles or fields reveal candidates that match astrophysical observations, explore parameter space of beyond standard model physics? Consciousness and quantum mechanics sometimes intersect speculatively. Some theories propose quantum effects in neurons contribute to consciousness, microtubules in brain cells maintaining quantum coherence, creating computational capacity beyond classical neural networks. Most neuroscientists are skeptical. Brains are warm, wet, noisy, exactly the environment where decoherence is rapid. But quantum biology has revealed quantum effects in photosynthesis, bird navigation, enzyme catalysis. Maybe brains use quantum mechanics subtly. Quantum computers won't directly answer whether consciousness is quantum, but they might clarify what computational problems require quantum effects, whether classical neural networks capture everything brains do, or whether some cognitive capabilities need quantum resources. And there are stranger possibilities. Simulating early universe conditions quantum mechanically, modeling quantum information in black holes to test holographic principle predictions, exploring whether quantum computation has limits we haven't discovered. Maybe complexity classes shift when you actually build the systems, revealing constraints theory missed. The barrier breaking doesn't just enable applications, it creates an experimental platform for quantum mechanics at scales and complexities previously impossible. Laboratory universe where we control quantum states precisely. Observe phenomena theory predicts, but nature rarely isolates. What patterns emerge in large entangled systems? What phase transitions appear as quantum algorithms scale? What happens at the boundary between quantum and classical, the region where decoherence becomes partial rather than complete? We're building microscopes pointed at quantum mechanics itself. What we see might surprise us, might refine theories, might reveal phenomena we didn't know to look for. The questions sharpen, and with them reality becomes more detailed, more strange, more itself. There's comfort, strange as it might sound, in recognizing that barriers are temporary. What feels fundamental, inevitable, insurmountable, often reflects the current edges of our understanding, not the ultimate boundaries of possibility. History is full of limits that dissolved when perspective shifted, when new tools emerged, when accumulated effort finally exceeded the threshold. Heavier than air flight was proven impossible by respected scientists, right up until the Wright brothers flew. Breaking the sound barrier would destroy aircraft, experts claimed. Until Chuck Yeager didn't disintegrate, computing machines couldn't be general purpose. Then Turing showed they could. Each generation encounters barriers that feel absolute, and some are. The speed of light genuinely limits information transfer. Thermodynamic limits genuinely constrain efficiency, but telling which limits are fundamental and which are provisional is difficult while facing them. Quantum error correction felt fundamental for years. The mathematics said it should work, but reality kept refusing. Error rates stuck above threshold, systems failing to scale. Reasonable researchers wondered if some deep aspect of quantum mechanics or thermodynamics imposed barriers the math didn't capture, and then the barrier broke. Not dramatically, not with paradigm-shifting revelation, but through patient accumulation of improvements. Better qubits, better isolation, better calibration, better control, each contributing fractional progress that compounded over time. The lesson isn't that all barriers fall eventually, some won't. The lesson is humility about which limits are fundamental and which are contingent. The universe is larger in possibility than our current theories suggest. It accommodates more, permits more, contains more strangeness and capability than we can see from any single perspective. This could be anxious. If we can't trust that limits are real, how do we know anything? But it can also be calming. The problems that feel insurmountable today might not be permanent. The mysteries that seem impenetrable might yield to tools and perspectives we haven't developed yet. Sitting with uncertainty, accepting that we don't know what's possible and what's not, becomes an act of openness rather than resignation. The universe will reveal what it permits in its own time, through our patient exploration, and sometimes, quietly, in laboratories cooled to near absolute zero, it reveals that something we thought impossible is just difficult. That's enough to wonder about. Let's return once more to the human story behind this breakthrough. The patience required to chase impossibility. Quantum computing research spans decades. Thousands of physicists, engineers, mathematicians working incrementally, publishing papers describing tiny improvements, failures carefully documented, successes modestly celebrated, each advance measured in fractions of a percent, error rates dropping from 1.2% to 1.1%, coherence times extending from 80 microseconds to 100 microseconds, calibration procedures refined to reduce crosstalk by 0.3%. Individually, these feel small, almost trivial. Collectively, compounded over 20 years, they crossed a threshold that transforms the field. There's something beautiful about this patience. No single heroic breakthrough, no eureka moment, just accumulated effort, people dedicating careers to shaving microseconds off decoherence time, improving gate fidelity by basis points, developing algorithms that squeeze marginally better performance from imperfect hardware. The barrier broke quietly because it broke gradually. Willow's result is the first clear demonstration, but it stands on foundations built by hundreds of research groups, thousands of experiments, millions of hours of careful work. Most of that work is invisible. Failed experiments don't make news. Incremental improvements don't trend on social media. The researchers who spent years optimizing one component of one type of qubit, enabling someone else's experiment to succeed, their names aren't known outside specialist circles. And yet, this is how barriers break in reality. Not through singular genius, but through collective, sustained effort. Communities of researchers building on each other's work, sharing techniques, replicating results, pushing together against limits that no individual could move alone. The patience is both temporal and psychological. Temporal, decades from idea to demonstration, with no guarantee of success. Psychological, continuing despite setbacks, failed experiments, funding challenges, skepticism from peers. Quantum computing could have failed. The barriers might have proven fundamental. All that effort, all that patience, could have revealed an impassable limit, but it didn't. The effort was enough, the patience paid off, and somewhere, in a laboratory colder than space, qubits maintain coherence for milliseconds while error correction heals their decay. And people who spent careers building toward this moment watch data confirming it works. The universe permits this. After all the effort, after all the patience, after all the uncertainty, it permits it. That feels like grace. Even with quantum computers, even with barriers broken, some mysteries persist. The halting problem, determining whether an arbitrary program will finish or run forever, is undecidable. No computer, classical or quantum, can solve it generally. This isn't an engineering limitation. It's proven mathematically impossible by Turing. Expanding computational power doesn't eliminate undecidability. Gödel's incompleteness theorems show that mathematical systems complex enough to describe arithmetic contain true statements that can't be proven within the system. If mathematics is incomplete and the universe is mathematical, does reality contain facts that are true but unprovable, even in principle? Quantum mechanics itself remains philosophically mysterious. We have equations that work perfectly, predictions confirmed to extraordinary precision, but what measurement is, why observation collapses superposition, whether many worlds exist or wave functions are real, these remain open despite a century of quantum theory's success. Consciousness poses its own unknowability. We don't understand how subjective experience arises from physical processes. Quantum computers might contribute insights, might simulate neural processes with quantum precision, but whether that explains qualia, the redness of red, the painfulness of pain, the experience of being, is unclear. Some questions might not have answers we can comprehend, not because we're not clever enough, but because the answers require concepts we can't form, perspectives we can't access, modes of understanding beyond our cognitive capacity. Like explaining color to someone who's never seen. There's no translation, no description that captures the experience. Maybe some truths about reality are like that, irreducible to forms our minds can grasp. This isn't pessimistic. It's acknowledging that the universe is larger than us, older than us, stranger than us. Our understanding is partial, always will be partial. That's okay. Expanding what we know doesn't eliminate mystery, it relocates it, reveals deeper layers of strangeness beneath the strangeness we've tamed. Quantum computers cross barriers in simulation, optimization, certain computational classes, but they don't make everything knowable, don't resolve all questions. don't eliminate wonder. If anything, they deepen it by revealing how much stranger reality is than we suspected, how much capability the universe permits, how many layers exist beneath classical appearances. The barriers we cross reveal landscapes beyond, stretching toward horizons we can't see, containing mysteries we haven't formulated yet. And that's beautiful. A universe that retains the capacity to surprise us, to exceed our understanding, to remain perpetually inexhaustible. We learn, we discover, we build, and the universe keeps its secrets, sharing some while withholding others. The balance feels right somehow, enough knowable to sustain curiosity, enough mysterious to sustain humility. So here we are, you and I, at the end of this exploration. We've drifted through quantum mechanics, particles in superposition, entanglement across distance, decoherence destroying fragile states. We've walked through laboratories where engineers battle entropy, cooling systems to near absolute zero, isolating qubits from the universe's chaos. We've watched a barrier break, not with drama, not suddenly, but through patience compounded over decades, error correction working, logical qubits outliving physical ones, exponential suppression finally crossing the threshold from theory to reality. We've speculated on what becomes possible, molecules simulated quantum mechanically, materials discovered in possibility space we can't currently explore, problems solved that currently seem intractable, and acknowledged what remains mysterious: consciousness, quantum interpretation, limits that even expanded computation can't transcend. The universe, it turns out, is generous in unexpected ways. It permits quantum computers despite how fragile, how improbable, how difficult they are. It allows barriers to break when we didn't know if they could. It accommodates both expansion of knowledge and persistence of mystery. And you, perhaps you're drifting towards sleep now, or maybe just towards stillness, toward a quiet space where thoughts slow and breathing deepens. The questions we've explored don't need immediate answers. Tomorrow's challenges can wait. The barriers yet to break will still be there, waiting for the patient accumulation of effort, the slow compounding of improvements, the moment when threshold is finally crossed. For now, there's just this: the recognition that reality is stranger and larger than we suspected, that impossible things sometimes become possible, that the universe keeps revealing itself in layers, sharing secrets gradually while retaining its essential mystery. You can rest in that. The not knowing, the uncertainty, the wonder at what might come next. These aren't problems to solve. They're the texture of being alive in a universe that remains endlessly surprising. So let your thoughts slow, let your breathing deepen, let the questions drift away, unresolved, patient. The quantum states will keep evolving, the universe will keep computing itself, and you can rest knowing that barriers break, mysteries persist, and tomorrow offers another chance to wonder. The universe permits this, permits you to stop grasping, stop striving, stop needing to understand everything right now. It permits rest, it permits peace, good night,